So 8.4, solving exponential equations with like bases. And just as a quick review, just so we can remember what a base is, the base is the number that's being repeatedly multiplied by itself in an exponential situation like this one, okay? The 4 here, that's the exponent or the power, you can call it. That's how many times the base is being multiplied by itself. So if we were to rewrite this in its expanded form, you'd have a 5 multiplied by itself 4 times. 1, 2, 3, 4. See that? So this, and I think we talked about this, maybe I'm thinking of a different class, but repeated multiplication it can be simplified with exponential form, just like multiplication is just a simplified form of addition, and addition is just a simplified form of counting, okay? So at its roots, really, exponents is just a really simplified form of counting, I guess, or grouping, if you want to put it that way. So with the name being, we're going to solve equations with like bases, we are going to see equations, right? So we're going to see some equal signs, but what we want is we want to look at bases that are the same, like 5 and 5. If for some reason the bases don't match like this, we're going to have to force them ourselves to match, okay? So this is why this is important, okay? Because if you can force the bases to match, if you can force them to match, you can ignore the bases, just like this example shows, right? You got a base 2, power of n, power of 5. Well, ignore the bases, just look at the exponents. If you can get n to equal 5, and then, of course, there'd be a little bit more work. Usually it's like, I don't know, n plus 3 here. Then you'd solve that, right? And you say, well, n plus 3 got to equal 5. Then you'd solve that equation. See what I'm saying? But at least we could ignore those bases, because we don't have to think about this in terms of exponential format, saying, oh, I'm going to graph these until they match. Well, that would suck. Where if we use this like bases property, things can go pretty quick, if we can just force the bases to be the same, okay? Now this one, the bases don't match either, but the nice thing is I know that 1 million I can write as a base 10 exponential, okay? So I'm not really dealing with the 10 to the power of n right here. All I'm trying to do is force this 1 million to be a base 10. Now this actually goes back to lots of different lessons that we've had in this class, and a lot of what mathematics really is. If you can just change things in mathematics to be something else, something that you want it to be, then you have a great tool in your math tool belt to use, and you can use it on almost anything, right? So as long as you know, hey, I can change 1 million and change it into base 10 like this one, this lesson goes pretty quick, okay? Because this would be 10 to what power? That's how many zeros are there? 1, 2, 3, 4, 5, 6. 10 to the power 6, okay? Well, if you're not sure that that does equal 1 million, then put that in the calculator, 10 to the power 6, until you get some kind of matching value on this one. On the other hand, and I'm going to show this, I'm showing this purposefully because it kind of sucks, which hopefully leads you to not use this method. But if you're like, look, I'm going to change 1 million into base 10 right here, you could say, look, I'm going to change it into scientific notation, which we all love. And you'd say it'd be 1 times 10 to what power? So then you'd be saying, well, how many times would I have to move that decimal in order to make that 1 right there? Well, you'd have to move it 1, 2, 3, 4, 5, 6 times. So you get 1 times 10 to the power 6. Just make it a phantom 1 at that point. See how we got 10 to the power 6 right there? Okay. I hope you enjoyed that as much as I did. But in any case, now that the bases are the same, ignore them. You got n equals 6. And this one doesn't require any more calculation. It's done. Could you check? Could you check? Yeah, sure. Replace the n with 6. See what you get. 10 to the power 6. Does it equal 1 million? Now, before I continue with this, I don't want you to get the idea that I'm making these 10s phantom 1s. That is not what I'm doing, okay? I'm just using a principle that says, since the bases do match, really all you're trying to get is the exponents to match, which of course would force the total values to be the same, okay? All right, this one also, the bases match. Hey, no problem, man. That's a doable one right there. And so, since the bases match, they're both 3s right here, ignore them. And just rewrite these as a new equation. N minus 5 then would equal 5n minus 1. Well, this now is an equation. Like I said before, we're looking at an equation that we need to solve. So principles of equality here. You know what? I'm going to put the ends on the right. A little variety today. It's a nice Christmas present for you guys. But I'm going to add 5 to both sides. No, I want the numbers on the right, don't I? I'm going to add 1 to both sides. That's better. Okay, so that's going to zero that out. Negative 5 plus 1 is negative 4. But also, simultaneously, I'll subtract an... I'll show that as a 1n right there, minus 1n. 5n's minus 1n, that'd be 4n's right there. Okay, so I got negative 4 equals 4n. But really, I don't want 4n's, I just want 1n's. So how do I make a 4n a 1? Just divide it by 4. Divide it by itself. And then negative 4 divided by 4 is... Oh, dang it. Negative 1, that's better. And then I'll just make that coefficient of n a phantom 1 right there. Now, before we say, hey, this is good and done, let's just check to make sure this works. Okay? Because, I don't know, maybe it's kind of like a magic trick. People just don't believe me here, but I got 3 to the power of n minus 5, right? This needs to equal 3 to the power of 5n minus 1. Okay, but now we're saying, we're pretty sure n is negative 1. Hopefully we did that right. We'll find out. Okay, so I got negative 1 minus 5, and then 5 times negative 1 minus 1. Now, just from the order of operations, I'd have to be working inside the exponents first. So negative 1 minus 5 on the left side, that'd be 3 to the power of negative 6. And on the right side, I'd have 5 times negative 1 is negative 5 minus 1, negative 6. You see how we get matching terms right here? Now, I don't really care what that value is. It'd be pretty ugly as a decimal. I think that'd be pretty ugly as a fraction as well. But I can see that both sides match, and so I'm okay just saying, hey, look, we found the answer right there. That's our solution. And a solution to an equation is a value that you can replace the letter with in order to make the original statement, this one, a true statement. Now the bases do not match, right? We got a 1/5 base and a 625 base. And if you're like, what do you mean the 625 is a base? It has an exponent, it's just a phantom 1. You can keep it there if you want. I really don't care to see it. Whatever, all right? Well, this fraction, I don't know. Most people don't like fractions. And yes, fractions destroy lives. I don't really want that to be a fraction. I mean, you're welcome to have it be a fraction if you'd like. And so there's really 2 different ways to do this. I'm going to get rid of the fraction. And before you start thinking what the crap is going on here, again, I'm going to change the way that 1/5 to the power of n, I'm going to change the way it looks. I am not going to change its overall value, though, okay? Well, how am I going to do that? Well, I'm going to take the 1/5, and I'm going to reciprocate it. Well, why would you do that? Because, I'll keep it in parentheses, by the way. Because if I reciprocate this, like I just barely did, all I got to do is make my exponent negative, and it's just an n. Now I just flipped it. Now it's a negative n. And by doing this, I don't want to see that over 1, because remember, we don't like that fraction. Just make it 5 to the power of negative n. So I'll clean this up to make it look a little bit more pretty, right? There you go. 5 to the power of negative n. Now this still equals 625, and the 625 still does not have a 5 base on it, okay? And while there is some shortcuts, we haven't learned those yet. So I've got to take a kind of an alternate route here. I'm going to take the 625. I'm just going to keep dividing it by 5. How do I know it's divisible by 5? Because of the 5 and the 1's place value. Just divide it by 5, and we get 125. See, and I'm looking for base 5s on this one, which means that's why I'm dividing this by 5, because I want the bases to match, right? I want this to be a base 5, and this one to be a base 5. So I'm going to take 125 and divide it by 5, which would be 5 and 25. And we know 25 is, well, 5 times 5. Okay, so that's the 625. Again, I'm going to change the way it looks. I'm not changing its value. It's 5 to the power of 4. Okay, and this 5 to the power of 4, it equals the old base 5 that we had here. See if I just move this down. Now that my bases match, I can ignore them. And even though the 5 in purple there has parentheses around it, that's not going to make a difference. So really what I end up with is I got this negative n equals, well, the other base 5, but it's exponent 4. And for those that don't remember, that's the phantom 1 right there. I'm going to divide both sides by -1, which makes the coefficient of n now a phantom 1 equals -4, okay? Now, there's only one value to try in here, so I'm gonna test it out in my calculator. Parentheses, 1/5, close parentheses, but my power is just -4. I push enter, I get 625, it works, we're good there. So if you see fractions like this, that's what I would recommend doing. Some people would say you could have reciprocated the 625, you could have made it over 1, then reciprocated that to make the exponent negative. I wouldn't want to do that because you still have to do this kind of stuff right here. So we would want the base to be a whole value. We want to kind of try to avoid those bases that are fractions like that. All right, here's a good one right here. And I think it looks worse than it is. Now the problem with this one is you can take the 16, because remember that the objective right now is, I'm kind of ignoring the exponents. I got base 8 and base 16 right here. Okay, what I would really like is for my base 8 and base 16 to have the same base. Here, I'll do it over here. Now the problem with this is if I take 16 and I say, look, I'm going to divide it by 8, the other factor is a 2, which is prime. Okay, so the only way that I can change the base on this one is if I got 8 and 8 right there. And again, don't get this confused with addition. It's not addition, it's multiplication, right? So this means that I got to, not only do I have to change the base 16, but I also have to change the base 8 into what would be 4 and 2, right? There's a 2. And just seeing these 2's like this gives me a good target on what I would want my bases to be, because, you know, this 8 also is going to split up into 4 and 2, and 4 splittable up into 2 and 2. Splittable word? 2 and 2. There we go. So if I, just by changing those, again, I'm not changing the value. All I'm doing is changing the way they look. 8 would be 2 to the power of, there's 3 2's there. And 16 would be 2 to the power of, I got 4 2's right there. Okay. Now these aren't equal, so you know, don't get that confused with the equal sign. I'm just relating to where these were in relationship to the equal sign. Okay. So let's look. What do we got? Okay. So on the original problem, I'm not going to have a base 8 anymore. What I have is 2 to the power of 3. Okay. Now that would be in parentheses right here. It still has that exponent x plus 2, right? And this would equal 16, which was 2 to the power of 4. And its exponent was 4x plus 5. So this goes back to exponent rules for us. Remember, if you got an exponent on the outside of parentheses, we have to multiply that by the exponent that's on the inside of the parentheses. Now this is going to look a little different for us because I'm distributing kind of backwards what we saw with the exponent rules. I'm distributing the 3 exponent into the x plus 2 and the 4 exponent into the 4x plus 5. Okay, so what does this give us? The bases are still the same, and you could even kind of ignore those at this point with the distribution, but I'm going to start on the left here. 3 times x would be 3x, and then 3 times 2 would be 6. That's positive 6, so plus 6. And then the 4 in red distributed, that exponent multiplied by 4x's would be 16x's, and then 4 times 5 would be positive 20. Okay, so there you go. The bases match now, which is exactly what we wanted. And now I'm just going to, all I'm going to do is compare the exponents, okay? So I got 3x plus 6. This would equal 16x plus 20. Well, all we got here now is an equation that we need to solve. So this one, you know, I'll put the x's on the left this time, numbers on the right. So subtract 6. And again, it wouldn't matter if you put the x's on the right side, either of you guys. That's going to zero out the 6 there, but I'm going to, so 20 minus 6, that's 14. I'll also zero out the 16x's, so minus 16x's. Okay. That looks like it's negative 13x's. So negative 13x's equals 14. Just divide both sides by negative 13 here. Kind of an ugly fraction, but it'll do. X here equals negative 14/13. Okay, now again, you can check this. Let's see what happens. So I'm going to replace in the first one, I have 8 to the power of, that's a negative 14, and I can even use the fraction button in my exponent. Negative 14/13 plus 2. Now, this may look ugly when I push enter, because I haven't pushed enter yet. It may look pretty ugly. Let's find out. If it is, I don't really care. It is ugly. 6.817443171. But I'm going to try the other side. I got base 16 to the power of 4 times that ugly fraction, right? Negative 14/13. And that is plus 5. So I push enter. Yeah, it's the same exact ugly decimal, 6.817443171. And that confirms that x equals negative 14ths is the solution to our original equation, even though it was an exponential equation. I really do hope that you guys doing these, because this is, I'm not saying it's advanced stuff. All it is just doing the same thing we're doing, but now with exponentials, okay? But if you can do this kind of stuff, again, if you can just understand that you can do stuff with numbers without changing values, you can change the way things look without changing values. Really, calculus wouldn't be that hard for you once you can grasp that fully, okay? Now, on this one, we got a base 2 and a 2 to the power of x. There is a couple different ways to do this, but the first thing I would want to do is just isolate my base 2 to the power of x. That means I don't want this 2 being multiplied by it. So right here, I'm going to divide both sides by 2. Okay, that's going to make that a phantom 1 there. So I'm left with my 2 to the power of x, and we don't really need that in parentheses, but 64 divided by 2 is 32. Okay, so this goes back to one of the earlier problems. All I got to do now is make that 32 a base 2, right? So I'll start by just dividing 32 by 2. 2 and 16, there's 2 and 8. And if you're worried that these values are going to come out not, I guess, convenient like a base 2 kind of thing, don't, because as mean as math people can be, I didn't see that the assignment does that pretty bad. So that's 2 to the power of 1, 2, 3, 4, 5. 5 2's there, and that's a 2 to the power of x. You know what, I'm going to get rid of those parentheses just so we can see that the bases do match. But that's good enough to say that x equals 5 right here. And let's check. So that'd be 2 to the power of 5. We know that's 32 because we just did this work here. And then times 2, that's 64. So I didn't even need a calculator to check this stuff. I'm not saying you can't use a calculator. You should if you need to, but this saves a little time. All right, so this one's like the other fractional problem we saw, the 1/5 and 5 stuff. I don't like this 1/10 right there, and I hope you don't either. Not because well, it is kind of because we're prejudiced against fractions, but we don't care. So on this one, I'm going to take this 1/10 and I'm going to flip it, okay? It's just if I do that, really what I've done is made that 10 to the power of, again, you could look at this like it's 10 to the power of -1. Again, that 1/10 and 10 to the power of -1, they have exactly the same value. They're just shown differently. And then we could say, look, you got the x minus 8, right? Now we're looking at a situation where I'd be distributing this -1 into that parentheses, and -1 times x would be -1x. And -1 times -8 would be +8 now, right? So I've got base 10 to this exponent, and then I also got this other base 10 to this exponent, 4x plus 2. And this is good enough for us to say, now that the bases match, that we're going to go in and just rewrite the equation without the bases. Okay, so let's go ahead and do that. I got the -1x. You could just make that -x, by the way, but we're going to have to solve this anyways. Equals the other exponent, 4x plus 2. If we can make these equal, then we should get a true statement in the end. So, solving this one, we'll say, yeah, we'll still keep the x on the left, numbers on the right. So that means we have to subtract 8 from both sides. I know I'm doing this kind of fast, and I feel like I'm doing it kind of fast. That's on purpose, just because we've seen a lot of this stuff before. Subtract 4x's to zero this one out. -1x minus 4x's would be -5x's. So 5x equals, -5x equals -6. We'll divide both sides by -5. And I get x equals, oh, use a different color there. Divided by -5, there we go. And I get x, that's 1x, phantom 1x equals positive 6/5. Okay, so I got an x value that's 6/5. Let's see if this will work. So I'm going to use the storage button as well, 6/5 stored for x. So that's 1/10 in parentheses, close parentheses, to the power of x minus 8. When I get that, oh, that's a big number. 6,309,573 and some change. That's what I got. Now let's see if we get the same thing on the other side, because we should. But that's 10 to the power of 4x, and remember x is 6/5, plus 2, enter. Oh, it is 6,309,573. It is exactly the same, which means that x equals 6/5. Yeah, that's our solution right there.